Variation functions. Our objective is to solve problems involving direct, inverse, joint, and combined variation. Why learn this? You can use variation functions to determine how many people are needed to complete a task, such as building a home in a given time. Let's start with direct variation. That's when you have y equals k times x. For this to work, k can't be 0. K is your constant of variation. It's the thing that doesn't change. Your x and your y are your variables. They're your xy coordinates, if you will. So let's practice using them. So we're going to write and graph direct variations. So we're given y varies directly as x, and y equals 14 when x equals 3.5. So we're going to write and graph the direct variation function for that. So let's start with our y equals k times x. Our y is 14 when x is 3.5. We don't know what our k is, but to be able to create a graph, we need what k is. So we're going to solve for k. So to do so, we divide both sides by 3.5, which gives us the fact that k equals 4. So now if we write our direct variation function, we have y equals 4x. And when you graph this, you start at 0, and you rise 4 and run 1. So now let's try solving direct variation problems. The circumference of a circle C varies directly as the radius r, and C equals 7 pi feet, when r is 3.5 feet. So we need to find r when the circumference is 4.5 pi feet. There are two ways you can do this. You can use your direct variation function. We're just going to use c and r instead of y and x. So we can go c equals k times r, which means we have 7 pi equals k times 3.5, leaving us with k equals 2 pi. We can then substitute that back in, so we'd have c equals 2 pi times r. And since we're looking for r when c is 4.5 pi, we'll stick that back in. So we have 4.5 pi equals 2 pi r, which means your radius is going to be 2.25. The other way you can do this is to solve or write and solve a proportion. So to do so, you would have your first c over your first radius equaling the second circumference over your second radius, and then you can cross multiply and solve for r. So that would mean you'd have 7 pi over 3.5, because your circumference of 7 pi goes with your radius of 3.5, and that's going to equal 4.5 pi over your unknown value. And when you cross multiply, so multiply 4.5 pi times 3.5 and then divide by 7 pi, you end up with r equals 2.25. So either way, it brings you to the same ending. Now let's look at a joint variation. A joint variation is a relationship among three variables that can be written in the form y equals k times x times z. Once again, k is your constant, and your variables this time are going to be x, y, and z. So y varies jointly as x and z. Let's practice solving joint variation problems. The area A of a triangle varies jointly as the base B and the height h. And A, so our area equals 12 meters squared when our base is 6 meters and our height is 4 meters. We want to find B when our area is 36 meters squared and our height is 8 meters. To do this, we can use our joint variation. So we would have A equals our constant times our base times our height. So we would have 12 equals K times 6 times 4. And when we solve for K, we end up with 1/2. We can now substitute that back in. So we have A equals 1/2 our base times our height. Hey, that should look kind of familiar. And then we can substitute in our other pieces of information. So we have 36 equals 1/2 our base times our height, which was 8. So 36 divided by 4 is going to give you 9. So your base is 9 meters. The third type of variation is inverse variation. This describes a situation in which one quantity increases and the other decreases. You can think of it as y equals k divided by x, or x times y equals k. We technically just solved for k in this one here, so we multiplied both sides by x. X and y are still your variables, and hey, k is still your constant of variation. Nothing new there. So let's practice writing and graphing inverse variation. Alright, so we're given that y varies inversely as x, and y equals 3 when x equals 8. So we're going to write and graph the inverse variation function. So remember, inverse is y equals k divided by x. So we want to find our value of k. So if y is 3 and x is 8, solving for k means that k is going to equal 24. So now we can write the inverse variation function, which happens to be y equals 24 divided by x. You can use a table to help you graph. So plug in each of these values in for x and simplify and get your answer. So when you do so, you end up with these numbers. Once you have your table, it's good, by the way, to make sure you pick some negative and positive values, because when you graph, your graph is not a direct straight line. It's inverse. It's taking an indirect route somewhere. Okay? So it's no longer a straight line like a direct variation. So using that knowledge, let's try doing a community service application. The time t that it takes for a group of volunteers to construct a house varies inversely as the number of volunteers, v. If 20 volunteers can build a house in 62.5 working hours, how many volunteers would be needed to build a house in 50 working hours? So we have t equals our constant divided by our volunteers. So our time is 62.5 equals our k divided by 20, because it's 62.5 hours for 20 volunteers. And when we solve for k, we end up with 1,250. Stick that back in. So now we have t equals 1,250 divided by our volunteers. And they said, okay, well, how many volunteers would be needed to build a house in 50 working hours? So that's your time. So we're going to replace our time with 50 and then solve for v. So we would need to multiply both sides by v and then divide by 50. And that would give us v equals 25. So you would need 25 volunteers instead of 20. Alright, so we've talked about direct variation and inverse variation. If we solve for k, this will help us be able to look at a set of data and determine whether it's a direct variation or an inverse variation. So if it's a direct variation, the constant ratio, it will be the same. Meaning when you take y and divide it by x, all of those values will be the same number. For an inverse variation, notice we solve for k, that's going to be a constant product. So when x times y gives you the same number each time, you've got an inverse variation. Let's practice. So let's determine whether each set of data represents a direct variation, an inverse variation, or neither. So let's look at this first one. Well, based on the numbers, the way they kind of look like, what we're going to do is we're going to go, okay, well, let's try seeing if when we divide that gives us what we're looking for. If not, then we'll try multiplication. So we have 9 divided by 3, which is 3. 24 divided by 8, which is also 3. And then we have 30 divided by 10, which is 3. So therefore, when we take our y and divide it by x, it gives us the same constant change. It's consistent. So therefore, this one is going to be a direct variation. Take a moment and try B on your own. When you return to the video, the answer will be revealed below. So as you can see, when you do y divided by x, you don't get the same number each time, so it's not consistent, it's not constant. So therefore, it can't be direct. So let's try inverse. So when we multiply x times y, we get 36 each time, so therefore, it's an inverse variation. Alright, now let's look at a combined variation. A combined variation is a relationship that contains both direct and inverse variation. Quantities that vary directly appear in the numerator, and quantities that vary inversely appear in the denominator. Okay, so the volume, V, of a gas varies inversely as the pressure P and directly as the temperature T. A certain gas has a volume of 10 liters, a temperature of 300 degrees Kelvin, and a pressure of 1.5 atmospheres. If the gas is compressed to a volume of 7.5 liters and is heated to 350 degrees Kelvin, what will the new pressure be? So for this, we're going to have V equals, and then we have K times T over P, as we have our temperature and our pressure inversely and directly. And now we can fill in our information that we know from the other one, because we want to find K. Our goal is always to solve for K and get whatever the constant is. So in this case, we have 10 equals K times 300 divided by 1.5. And when we solve for K, we get 0.05 equals K. Substitute that back in. So it's substituted back in, and now we're going to use our volume and our temperature for what we have to figure out our pressure. So our volume ends up being 7.5, and we have 0.05. Our temperature is at 350 degrees Kelvin instead, and then we have our pressure. So now we simply solve for P. So we want to get P by itself, and when we do, we end up with P equals 2.3. And that ends our lesson on variation functions.